This is probably the most important concept that we're going to do all year. Physics 12, a great deal of the time, we're going to be dealing with two dimensions, with what we call vector mathematics. And so it starts today. You might recall from last year that in physics, all measured quantities are either scalars or vectors. And in Physics 11, we weren't that fussy because our usual approach was if direction mattered, we would just let one way be positive and one way be negative. This year, we're not going to have stuff moving in a nice straight line. We're going to be moving in two dimensions, and so we're going to have to formalize some rules. Scalars have magnitude only, size. Put your pencils down and look up. So on that despicable me note, vectors have both what and what? Usually we write magnitude and direction, so I'll do that. Yeah, vectors have both magnitude. They still have size, but direction matters. Let's look at a top view map here. Patrick the puppy goes wandering around his neighborhood as seen below. So he goes 3 meters here, stops, goes 2 meters here, stops, goes 4 meters here, stops, 4 meters here, stops, 2 meters here, stops, 4 meters here. Okay. Notice I drew, let me zoom in a little bit, although you have it in your notes. There's a series of arrows drawn on the map of the physics teacher's front lawn. Each arrow shows the magnitude, size, and direction of a series of successive trips made by Patrick the puppy. Arrows showing both magnitude and direction are called vectors. And one way to do vector mathematics, Sean, is to draw everything according to scale very, very carefully. We're going to try and do better than that. When Patrick reaches his final spot near the car door, how far has he walked? Karin, it depends on what you mean by how far. Do you mean distance or displacement? So the distance would be 3 plus 2 plus 2 plus 4 plus 2 plus 4. Let me write that down. I think I'm going to have to shrink my screen down so I can get the numbers on the same screen. The distance is going to be 3 plus 2 plus 4 plus 4 plus 2 plus 4, which is what? 19 meters? Anybody else? It's Carter. I don't trust him. Is it 19? Yeah? Direction is none. Distance is a scalar. Displacement. Remember, displacement is just the change in position. In fact, if you want the displacement, it would be that arrow right there. And so the real question is, I'll magnify it here just so you can see it. How the heck can I figure out the magnitude and the direction of that? I'll give you a hint. I can use trig. Looking at Patrick's journey, looking at the map, how long is that arm? Loud and proud? Is it? Cool. How long is the top arm? Is it 4? Got moving numbers around in your head? See it? And this angle here is 53 degrees. Color, 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 color. I can find the magnitude. I'll use D with the vector sign for displacement. First of all, how will I find the magnitude, how big that is? I can go Pythagoras, get your calculator out, or you might be able to do this in your head, but it's going to be 3 squared plus 4 squared equals, and then square root I think it's going to work out to 5 exactly. This is the famous 3, 4, 5 Pythagoras Triangle, which a few of us nerds have memorized. So the displacement is 5 meters, but that's the magnitude. Displacement is a vector. All vectors have both magnitude and what? Direction. The direction, we would put a little at symbol to show that we're going to do a direction. That's an at symbol that I just have trouble drawing as a lefty. And we would say 53 degrees east of north. We will never use northeast or southeast. Those imply an exact 45-degree angle. Now, if you're wondering how the heck I came up with east of north, patience, later in the lesson or later today. I'll walk you through how we do that. But we would say the displacement was 5 meters in a direction of 53 degrees east of north. There are 2 ways to indicate that something is a vector. In diagrams or in handwritten notes, we put a small arrow above the symbol for a vector quantity, like I did here for displacement. Although we get lazy, it used to be that you did a complete arrow, and over the years, we've just become lazy and we just do kind of the half arrow. In textbooks, they'll often use a bold font to show a vector, but when I'm handwriting, to show a bold font is really tricky. There, that's bold font. So when we're handwriting, we use the vector symbol. Okay. You may notice that sometimes plain italics in a textbook without the bold font will be used if we're only referring to the magnitude. Again, that's tricky to write. So what we'll often do, if all we care about or all we want to report is the magnitude of a vector, we'll put it in an absolute value sign. And that's really what absolute value means. You learned it in math either last year or this year a little bit. What's the absolute value of 6? 6. What's the absolute value of 9? 9. What's the absolute value of negative 6? 6. What we were really saying is, what's the magnitude of that number's distance from 0? That's really what absolute value means. So, scalars and vectors. The challenge now is going to be that the mathematical rules for adding vectors are very different. If you add 3 kilograms of sugar to 2 kilograms of sugar, you get 5 kilograms of sugar, no surprise. If you add 3 liters of water to 2 liters of water, you get 5 liters of water. Masses and volumes are added together by the rules of ordinary arithmetic, because mass and volume are scalar quantities. They have magnitude, but no direction, much like your futures. Other scalar quantities include, so does anybody remember some scalars from last year, from Physics 11? One of them was a variable that was never allowed to be negative. I saw in the sci-fi show that no, it was never allowed to be negative. Remember? Starts with the letter T. Time. Can I abbreviate? Okay. Mass, which I already mentioned. Okay. Speed was a scalar. What was the vector equivalent of speed? Velocity. If I was a good teacher, I'd have a dumb way for you to remember that speed is a scalar and that velocity is a vector. I'd have some clever way for you to remember that. Karin, I got nothing. I'm a terrible teacher. Other scalar quantities that you'll learn, if we're lucky, we'll get to it this year. Voltage is a scalar. Work and energy, which I hope to get to this year. I didn't get to it with you last year. It's usually the last unit I get to, but spring break, we went a bit slower after spring break. You will need to memorize which ones are which this year, but Aiden, as long as you're doing the homework, you will. I don't think you'll need to set up flashcards or little things like that. If the day before the test you're still hazy, then fine, set up some flashcards, but I'll be flogging it to death during the year. If you add a 3-meter displacement to a 2-meter displacement, the two displacements may add up to 5, but they could also add up to 1. 3 meters to the right plus 2 meters to the left gives you a magnitude of 1 to the right. And they can add up to decimal values in between. 3 meters to the right plus 2 meters up, you actually end up having moved 3.6 meters. In figure 5.3, right here, I added those together using the rules for vector addition, and that's going to be the theme of this lesson. And as you can see, the resultant really depends on the directions of the vectors. For example, if I go 3 meters to the right and 2 meters that way, that's my displacement. In fact, basically, the smallest displacement I can have is 1. The biggest displacement I can have is 5. I can set up any decimal value you want in between. Give me enough time and I can tell you exactly what angle and what direction that 2 meter needs to be to give you any other decimal value that you want. Other vector quantities, remember force was definitely a vector because it mattered which way you pushed on stuff. Basically, when we were going winner minus loser last year, we were really using vector math. We were assigning one direction to be positive, winner plus, and one direction to be negative, loser minus. We'll still use something similar this year, but it may be two-dimensional, so we'll have to just expand on it. Acceleration was a vector because it determined whether you were speeding up or slowing down. If you did online learning after spring break, and not all of you did, but if you did the online learning after spring break, you might recall that momentum was a vector. Momentum was the physics of collisions. Head-on collisions are much worse than rear-end collisions. Believe me, direction matters. Okay. Let me see here. Well, velocity. So if I add together the force vectors of 7 newtons and 4 newtons, what's the maximum force I could possibly get? 11. What's the minimum force I could possibly get? 3. And I can get everything in between. Turn the page. Remember that 53 degrees east of north little dealio with Patrick the puppy? Here is how we're going to write vector directions. To show the direction of a vector, we focus on the angle where it originates from. So I'm going to zoom in. Here is an angle. See it? Here is how we're going to do direction. I always will draw a little compass rose somewhere anytime I'm doing directions. It takes 1 second. Have I written something down, Cleo? Do I feel better? Am I more relaxed? And you've already had me long enough to know I'm big on that. But also the number of times I've made a dumb mistake with directions. If you were watching very closely, you even noticed with Patrick the puppy, I started out going to the west. And then when you said east, I went, oh yeah, it's east, because I was dumb. I didn't draw a compass rose there. I should have. Okay. See this 28-degree angle? Do you notice that it's made up of one slanty line and one line that's at a nice right angle? See it? Okay. Here is how we write the direction. We would write 28 degrees, duh, blank of blank. So leave a space, write the word of. The last thing, the of, is always the direction of the nice right angle line. What direction is the nice right angle line pointing here? It's going to be of east. And then look up. What direction from east do I need to go to hit the slanty line? This is 28 degrees north of east. That's how we decided to do directions. Do the next one. I have just scrolled to a blank page, so I am going to go north, east, south, west. If you still have your compass rose on your page, you don't have to redo it. Okay? 51 degrees. What of what? North of south, east of west, what of what? Blank. The of blank is the nice line, the one that's at a right angle. What's the nice line at a right angle direction here? This one. North. It's going to be of north. From that line, the of north, which way do I need to go in order to hit the slanty line? This is 51 degrees east of north. I've got a compass rose still on the page, so I won't redraw one. So we're talking this angle right here. This is going to be 20 degrees north of south, east of west. What of what? Of what? What of north? West. You're going to have to wrap your brain around this. We'll practice it, but if you can't draw the vector in the first place, you're not going to be able to solve the question. Oh, sure, this will work. 48 degrees north of south, east of west. What of what? South of west. Start out going west. How do you hit that line? South of it. Oh, I've scrolled down. I have no more compass rose, so I'm going to do another one quickly here. 78 degrees north of south, east of west. What of what? Start out going south, go west of south. Oh, William, you were away yesterday. There is one mistake in my answer key on one of the quadratic equations. I accidentally put a negative in there. Remind me to tell you later. Oh, I got no compass rose. 52 degrees north of south, east of west. What of what? South of east? Hey, guess what? Each of these can be written in two different ways. Because I could also give you the same arrow by focusing on that angle. And that'll happen sometimes because maybe you started drawing your picture in a different order than I started drawing my picture. You're going to end up with the same magnitude and you're going to end up with the same direction. It's just that you happen to focus on a different angle. How big would that angle be? If the bottom one is 28 degrees, how big must that top one be? 52? 62? Because both of those will add to what? 90. The fancy word for that is they're complementary angles, hashtag nerd trivia. So I could also have called this 62 degrees north of south, east of west. What of what? East of north. I would give you full marks for either of those. So you're going to notice in my answer keys quite often I'll have two angles with two directions as the answer. Either of them you'd get full credit for. It just depends how you drew yours. Not only is 51 degrees east of north, but I could also have called this 39 degrees. What of what? North of east? Not only is this 20 degrees west of north, it's also 70 degrees. That's this one right here. North of south, east of west, what of what? North of west. Are you noticing any pattern, Sean? What? The directions swap for complementary angles, okay? So this one here is also 42 degrees, what of what? West of south. And this one here is also 12 degrees, and that would be this one right here, south of west. I'd give you credit for that. And this one is 38 degrees, that'd be this angle right here, east of south. So just get used to either a lot of my answer keys having both angles, or if I didn't put both angles but you got the complementary one, you can assume you're correct. So, vector addition in one dimension, I snuck in last year. What's 5 meters east plus 3 meters east? As a Freudian slip. Say one thing, but you mean another. What's 5 meters east plus 3 meters east? I usually put an @ symbol whenever I'm doing a direction, and the reason is W for west is also watts as a unit, and so I never am sure, oh, it's a direction if it's after an @ symbol. And N is newtons and N is north. Oh, if it's after an @ symbol, it's north. 6.2 newtons left added to 6.7 newtons right. 0.5 newtons. Okay. That third vector that we wrote, the answer, represents the sum of the first two vectors. We have a fancy term for that. We call it the resultant. When you add two vectors together, you get a resultant. So Mark, that should have kind of been familiar. That's what I was doing with the winner minus loser. We were actually doing example 3. I was building that in. 2 dimensions. We represent vectors with arrows. And one way of doing this, Ali, would be to very carefully draw everything to exact scale using rulers and protractors and graph paper, and then carefully measure the distance between them. Would work? So suppose John travels 5 kilometers west and then 8 kilometers north. What's his displacement? We could draw a scale diagram, or better yet, we could use trig. This is in bold font for a reason. This is the portion you'll need to commit to memory. To add two vectors together, we draw them tip to tail. Connor, how do I draw them? Tip to tail. I want to add two vectors together, Ali. How should I draw them? I got a hankering to add two vectors together. Mark, any suggestions on how I might want to draw them? Cleo, let's suppose you and I want to add two vectors together. Give me a suggestion. How should I draw them? How should I draw two vectors together? Everybody. How should I add two vectors together? Everybody. How should I add two vectors together? Everybody. I'm going to draw them tip to tail. Then the resultant is going to be from the tail of the first to the tip of the second. Say what? Look up. Here's a vector. Okay? Here's another vector. Let's make it look like that. If I want to add those two vectors together, I would draw them tip to tail. And the resultant is going to go from the tail of the first vector to the tip of the second vector, like that. Now, this is a very, very complicated one because there's no right angles here. We will eventually deal with ones where there are no right angles, but they suck. Most of the time this year, especially on the quarter system where I'm having to cut corners, everything's going to be at nice right angles. So typically what we'll have is a vector that looks like this, and I want to add it to a vector that looks like that. How should I add those together? Draw them. Everybody, draw them. So I would move the tail of the second vector to the tip of the first, and the resultant is from the tail of the first vector to the tip of the second vector. There's the resultant. How could I find the magnitude of the resultant? Really? How could I find the direction? Shift sine or shift cos or shift tan to get the angle, and then it's going to be north of south, east of west, what of what? See how we've been putting everything together now? Okay. Yeah? Let's try it. So example 4, you've all just turned the page. Example 4 was John travels 5 kilometers west and 8 kilometers north. So stay on example 4, but look at up here at my example 4. Sorry, stay on example 5, look on example 4. First thing I would do is this. Ding, 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 ding. Do you see directions? Do you see directions? Draw compass rose. If you raise your hand, Mr. Dewick, could you help me with number 7? And if I see directions and you haven't drawn a compass rose, I'm walking away. Okay? The first vector, 5 kilometers west, I'm going to draw an arrow pointing to the west. Freehand eyeball it. How big is that arrow? How many kilometers? Do you remember what I just said? It's 5. And I'm going to add to it. Oh, remember DALP? What did DALP stand for? Draw a little picture with lots of DALPing this year. Way more than last year. Way more. The second vector was 8 kilometers north. Is 8 bigger than 5 or smaller than 5? Twice as big or not quite twice as big? I'm going to eyeball it. I'm going to draw an arrow that's bigger than 5 but not twice as big. I don't know. Jump. 8. There is my vector equation. And it's a little bit weird. Put your calculator down. We're not done yet. Because, Mark, how do I add vectors together? Draw them. Say that very carefully. Draw them how? Tip to tail. So I'm actually going to put an equal sign. This is an equation. And the equal sign is going to look like this. 5, 8. There's my vector triangle. And the resultant is going to be from the tail of the first one to the tip of the second one. This here, I'll label it with D, vector displacement. And then the direction is going to always be from where the vector is starting from. The theta, the angle, does not go in the top left. It always goes where my vector is beginning from. Color, color, color. Now let's find the magnitude. How could I find the magnitude? How could I find how long this line is? The magnitude. Pythagoras. So I'm going to make a little note here. d squared equals 8 squared plus 5 squared. This is the hypotenuse, so I don't need to do any subtracting to get it by itself in Pythagoras. Get my trusty calculator out. Now I'll get my calculator out, Mark, but not until I've drawn the vector triangle. 8 squared plus 5 squared equals square root. I get 9.43. So here's my answer. Vector D, magnitude 9.43, and I think the units were kilometers. They were. But all vectors have both magnitude and direction, so now I need a direction. The direction is going to be, I'm going to find theta, angle theta. How will I find that angle? Trig. Color, if you haven't already. That 8, opposite, adjacent, or hypotenuse. That 5. Which trig function has an O and an A in it? Tan. What always goes next to the trig function? Theta. That's sitting where the angle is. Equals opposite, 8, over adjacent, 5. Who remembers, how can I figure out how big that angle is? What do I do on my calculator? It's going to be inverse or second function or shift. I'll have to put the 8 over 5 in brackets. I get a magnitude of 57.99, 58 degrees, I think, yes? Pardon me? I'm getting the magnitude of the angle, the size of the angle. Now I need to add the north of south, east of west, what of what? Sorry? North of west? Yeah. Is that okay, Wes? Are you lying? Okay. Put your pencils down, look up. I went 5 west first, and then I went 8 north. Suppose Aiden had been drawing his picture, and he went 8 north, 5 west. When you did the Pythagoras, you would still get 9.43, because it's still going to be 5 squared plus 8 squared. But you would have found this angle theta here. Do you know what that's going to end up being? Or 32 degrees west of north. That one would have ended up being the complement of the 52 degrees north of west. I'd give you full credit for that. Just you drew your different vector first than I did. Allie, did you have a hand up earlier? Okay. Thought I saw kind of this. How do we add 2 vectors together, Wes? Draw them. Good. And then the resultant from the tail of the first to the tip of the second. The theta always goes where the vector is coming from, not where it's pointing to. Suppose we're pushing on an object. The first force is 10 newtons due east. The second force is 6 newtons due south. What's the resultant? Hint. Draw a little picture. Okay, I can do this. Easy peasy. Aiden, what's the first force? F1, magnitude and direction. Just read it to me. And direction. Did you say east? I'm drawing a compass rose. Okay. You said 10 east? Yep. What's the second vector? Magnitude and direction. 6, a little bigger than half as long as 10. try and make your diagrams roughly to scale. They don't need to be exactly to scale, but it's kind of nice if the angle that you find looks about the size of the answer on your calculator. So 6 to me is going to be, I don't know, about like that. Aiden, I'd like to add those together. How might I draw them? You don't say. That's a clever idea. Oh, you clever lad. So it's going to look like this. Now, you could have drawn the 6 first and then the 10. Look up. That would look like this. Don't write this down. Can you see you get the same resultant in both situations? When in doubt, try and go in the same order. I'll usually go in the same order that they give me in the question, unless it's way easier to change the order. When will that happen? Patience. Sorry. When in doubt, go in the same order, or I always, if it's a really tough question, I draw the easiest vector first, and then I draw the ugliest vector next. You'll see what I mean by that later on this year. So the resultant is that. You know what? I'll call it F with a subscripted R for resultant force. Whatever you want to call it, I don't care. What's the magnitude of this force going to be? Well, F squared is going to be 10 squared plus 6 squared. What do you get? It's going to be the square root of 136, so 11 point something. Rounded off properly. 11.7 units. And that's Newton's not north. How do I know? Because it's right next to a number and there's no at symbol in front of it. I think I mentioned to you several times last year, we need more English letters in the alphabet. We're running out of letters. So N is taken up by a bunch of stuff, as is W. Actually, they're all taken up by a bunch of stuff. So direction, at. Where is theta going to go? Bottom right or top left? It's always where the vector is coming from. So top left, color, 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 color. You know what? I can already tell you north of south, east of west, what of what. What's the what of what going to be here? South of east. So I'll even leave a space and I'll go south of east. Now I just got to get the magnitude. Okay. That's 6, opposite, adjacent, or hypotenuse. What about that 10? I think this is the hypotenuse, is it not? Yeah. So I think adjacent. Mr. Duick, why don't you use the 11.7 to find? I could, but if I got the 11.7 wrong, means I'm going to get the angle wrong. And often that 11.7 will be a yucky decimal, and I don't want to round off and whatnot. So which trig function has the O and the A in it? Mr. Duick, will it always be tan? On easy questions, yes, usually. What always goes next to the trig function? The angle. What's the angle this time? A variable, theta. Equals 10 over 6 or 6 over 10? Opposite over adjacent. I think 31 degrees south of east. Or 59 degrees east of south if you had drawn the 6 first and then drawn the 10. But you'd still get the 11.7. Is that all right? Good. Karn, how do I add two vectors together? Draw them. Good. I like example 6. I like example 6. I like example 6. Example 6 is a nice question. we can start to do plane crosswind questions, airplane and crosswind questions, or this is also the mathematical equivalent of boats going across a river and being pushed up or downstream by the current. Okay? Josh M., can you start reading with a plane? Start reading to me. A plane is? Stop. Did you say north? I'm drawing a compass rose. That's all I wanted you to notice was as soon as I see directions. Okay. The only time I might get away with not is if I noticed everything was north. Then I'd let north be positive and south be negative, and I could probably do this like physics 11, but pretty sure I saw other directions there too. Okay. Here's our argument, and I think if you look at your formula sheet, I think I put this on your formula sheet. Here's what I said. The velocity of the plane through the air. Actually, how did I write it on your formula sheet? It's the second or third equation, that big one there. What did I say? V something plus V something equals... Loud and proud, what? Okay, the which way the engine is pointing, plus whatever the crosswind is doing, that's what gives us our ground velocity. By the way, in the industry, they call it the ground speed. They should call it the ground velocity because it is a vector. But because in the industry they call it ground speed, I'll use that term even though I cringe every time I do because it's ground velocity. It's a vector, for Pete's sakes. It's not a speed. But okay. So here's really what we mean. Look up. The airplane is flying due north. Here's the shadow due north. But there's a wind blowing east. Which way is east for you folks? To the left or to the right? So as the plane is traveling north, it's also getting pushed to the right. It's going to end up going up and right. How fast and at what angle? Got the argument? So here is my vector equation with variables. Underneath it, I'm going to rewrite the vector equation with pictures. I'm going to DALP. Josh, what was the plane's engine velocity, magnitude, and direction? So I'm going to draw an arrow pointing up, and I'll label that 132 plus. I encourage you, try and do your vector diagrams bigger rather than smaller. Every year there's some kid who's going to do their vector diagrams and they always get them wrong because you can't see how the angles fit together. So if you got the room, make it a biggish picture. Josh, what's the wind, magnitude, and direction? 44, roughly 1/3 of 130, roughly. So, yoink. Ish. When I add those together, the combination of those, William, is the ground velocity. How will I add those together? Draw them how? You don't say. So equal sign 132, yoink, 44. That's what they're asking me to find. Yeah? Good. Solve this one on your own. I'm going to freeze the screen. You can look up because every so often I'll unfreeze the screen and let's see if we end up in the same area. Sorry? Yeah, because you have to be different. Yeah. Mark, got it okay? This is what pilots used to do by hand. It's all software now, but 40, 50 years ago, this would have been part of your training if you were a jet airline pilot, because you would want to know. Now, what you would actually do is, instead of saying, which way is the wind going to blow me, which way is the wind going to push me, you would say, hey, which direction do I want to go? How do I need to point my plane into the wind, and how fast, so that when we get combined, I end up going in the direction that I want to go? In other words, you would be interested in this. In fact, you'd want to find out how you wanted to point your plane. How would I get the V engine by itself? How would I move the V wind over? What's the V wind doing to the engine? Adding. So how will I move it over? How do we add two vectors together? Draw them. How do we subtract two vectors? Patience. No, not tip to tail. Actually, you want the short answer? We don't. Instead, we cleverly turn it into an addition question. There is a subtraction rule, and if you're a nerd, I can show it to you if you really want. But, and in fact, when I was in university, I memorized the subtraction rule, and then I had somebody show me, look, dude, why would you memorize a whole second rule when with almost no effort you can turn any subtraction question into an addition question? How would I turn 5 minus 3 into an addition question? 5 minus 3 is the same as 5 plus what? 5 minus 3 is the same as 5 plus what? Instead of saying minus, can you use a word that starts with the letter N and sounds more mathematical? 5 plus negative 3. With a tiny bit of effort, we can turn any subtraction into an addition. And then, how would I add those together tip to tail? But I have to rearrange things first. I like example 7. I like example 7. Well, normally adding 3 vectors together is fair game. I'll probably pull it from my test this year because I got to cut corners somewhere. But I'm only going to say probably because this is my first Physics 12 in the quarterly system, and I don't know how smart we can go, how fast we can go. So I'll say I like this question, I like this question, I like this question, but I'll say it with some trepidation. Maybe. We're adding 3 vectors together. Okay. Cool. Other Josh, what's the first vector, magnitude and direction? F1. That's a magnitude and direction. Did you say south? I'm drawing a compass rose. I feel better. Okay. By the way, can you see how, especially for forces, if you're reading in a hurry looking for directions, you might accidentally think 5.5 north? Read carefully, please. That part, I don't know how to fix. Have I mentioned we've run out of letters and we need more letters? We really do. So what was the first one again, Josh? Read it. So 5.5 south plus... Read more carefully. 8.6 what? Thank you. The other east. Plus. Put your pencils down, look up once you've jotted that down. I don't know if you've ever noticed, when we're adding 3 plus 9 plus 7, there is no way to add 3 numbers at once. You add 2, get an answer, and then add the third one. Yes? There is no way to add 3 vectors at once. You add 2, get an answer. Well, that's a lie. There is a way to do 3 vectors at once, and I'll show you. But for now, by the way, if you were adding this and you were clever, why would you not go 9 plus 3? What would you probably choose to do first? Yeah, you do the 10 plus 9, 19. Sometimes you can pick and choose your order. See it? Which 2 vectors might I be tempted to add together first because it's going to make the question easier? The 2 souths. The first thing that I would do is I would say this is the same as 16.1? Yeah. Double check me. Is it 16.1? I would turn this question into 16.1 and then tip to tail. Oh, wrong way, Mr. Dewick. Geez. 16.1 and then tip to tail 8.6. And 8 is roughly half of 16, so I made the line roughly half as long-ish. How will I draw the resultant? From the tail to the tip. And this is forces, so I'll call it force resultant. Is that okay? Good, solve it. I'll freeze the screen. Think you're going to get a magnitude in the 18s, I hope. Everyone on YouTube is going to be, who's Carter? Well, fine then. I put a joke in, it's not even worth it, even though you don't get another joke for the rest of the year. Is it 18.3? Now, I'm doing these questions the way I would in my homework, in that I'm doing Pythagoras all on my calculator, and honestly, I can probably do the trig without even writing that down. On a quiz or a test, I would actually write out the Pythagoras because I've made dumb mistakes, and I would show every single step for finding the trig, right? How do I add 2 vectors together, Nicholas? Draw them. How would you subtract 2 vectors? We'll talk about that. But first, I've told you Foxtrot is one of my favorite comics. The author, Bill Ammond, actually has a physics degree, and the physics is accurate. So the nerd boy Jason, who I really identify with, go figure, they're playing football, and his older brother Peter says, "Jason, what pattern did I tell you to run? You said go 10 yards out and then 10 yards to the right. What pattern did you run? I went 10 root 2 yards at a 45-degree angle." And are they the same thing? If you add the vectors, sure. And they are if you add them together tip to tail. That is the correct answer. It's football, not math class. Why do you think I rounded to 2 decimal places? And then I think I showed you this one last year. Now Jason's the quarterback. Okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards. Then turn right and go 25 yards. Then turn right again and go 30 yards. Then turn right and go 30 yards. Then turn left and go 10 yards. Then turn left and go 15 yards. Then turn left and go 20 yards. Then turn left and go 50 yards, and I'll hit you with the ball. And if you do draw that tip to tail, 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 you do end up eventually exactly back where you started from. That is a vector sum of 0. So won't I be right back where I started? I can't throw very far. Oh, how do I add 3 vectors? I said to you that with numbers, it's impossible to go, you do 2, get an answer, and then do a 3rd. You can actually add 3 vectors simultaneously. You just add them tip to tail, tip to tail, tip to tail. So here's a vector. Here's another vector. And here's a 3rd vector. I would go like this. Tip to tail. Tip to tail. And the resultant is going to be from the tail of the first to the tip of the last. If I change this, there's your resultant. I don't think I'll ask you to evaluate one like that, but I think in today's homework, I'll ask you to DALP one like that. Did I say homework? Here we go. Short little assignment, and you can also